So in this lesson, radiation, let us see the contents. What are the things we are learning in the radiation topic? So this unit we have divided into two chapters. One is the fundamental aspects related to the radiation. Maybe in your intermediate level or in the first year physics you might have learned. Okay, just we recollect, and along with that, then radiation heat transfer we are learning. Okay, so in this particular unit, these are the contents we are learning. So we start this particular chapter with a discussion of electromagnetic waves and electromagnetic spectrum. Okay, so we focus our attention on thermal radiation only. Then we are introducing the idealized black body and black body radiation and black body radiation function together with Stephen Boltzmann law, Planck's law, Wien's displacement law. Okay, so this and all we are learning. Along with this, radiation is emitted by every point on a plane surface in all directions into the hemisphere above the surface. Okay. So the quantity that describes the magnitude of radiation emitted are incident in a specified direction in a space, so which is nothing but the radiation intensity. Okay, so the various radiation fluxes such as emissive power, irradiation. Okay, so that sort of things and all we are discussing. Then along with that, we are discussing the radiation properties of materials like the emissivity, absorptivity, reflectivity, transmissivity, okay, and their dependence on wavelength, the direction, temperature. This and all we are learning. Then up to here, up to Kirchhoff law, that will come under the basic fundamental concepts of your radiation, and after that, to study the heat transfer analysis through radiation mode of heat transfer, we need to know the shape factors. So what is shape factor? That and all we are learning. Then heat transfer between black and gray surfaces we are learning, and at the end, the last topic is radiation shields. Okay. So these are the contents of your radiation unit. Then coming to the introduction. So far we have considered the conduction and convection mode of heat transfer, so which are related to the nature of material involved and the presence of fluid motion and among other things. Okay. Now we turn our attention to the third mechanism of heat transfer, which is nothing but what a radiation. So which is a characteristically different from other two. Okay, little bit attention you have to focus to understand this particular physical mechanism involved in the radiation heat transfer. Okay. Then here, suppose consider a hot object which is suspended in a evacuated chamber, okay, vacuum, and whose walls are at room temperature, so which is shown in the figure 6.1. Okay, then the hot object eventually cools down and reach the thermal equilibrium with the surroundings. How come? You will get doubt. Now the hot object you have placed in a evacuated chamber. Okay, this is evacuated chamber. No fluid is here, no air is here, nothing. It's a entirely vacuum. You have placed a hot object inside this particular vacuum chamber. Okay, so after some time, if you see that particular hot object reaches to the thermal equilibrium with its surroundings, eventually cools down. Okay, so that is, it will lose the heat until its temperature reaches to the temperature of the walls of the chamber. Okay, then the heat transfer between the object and the chamber could have taken place, okay, by conduction or convection, because these two mechanisms cannot occur in vacuum. Okay, therefore the heat transfer must have occurred through another mechanism that involves the emission of internal energy of the object. The emission of internal energy of the object. So this mechanism is called what? Radiation. Okay, so the radiation differs from other two heat transfer mechanism, that is conduction and convection. Okay, so it does not require the presence of material medium. Okay, particularly the radiation does not require the presence of material medium. Okay, so if you see, the energy transfer by the radiation is the fastest and compared to the conduction as well as convection. So which is at a speed of light. So already I have quoted this at the very beginning of while we are discussing the modes of heat transfer. Okay, then which is also having one characteristic that it suffers no attenuation in a vacuum. So attenuation means a straight line path it follows, no slendering and all. Okay, so that is a characteristic of your radiation. Okay, then the radiation transfer occurs in solids as well as liquids and gases. So in most practical applications, if you observe, all three modes of heat transfer occur concurrently at various degrees. But we are assuming, so which one is predominating, that only we are focusing our attention. But in practice, if you go to the industrial analysis and all, okay, so there you need to consider the all modes of heat transfer. Okay, but in the undergraduate level or post-graduation level, so which node of heat transfer is dominating, that only we are concentrating, that only we are considering. Okay, so here the heat transfer through an evacuated space can occur only by radiation. So this is very very important objective question in the competitive exams. Do remember all of you. Heat transfer through an evacuated space can occur only by the radiation. The best example is that's how this particular energy of the sun so reaches the earth by radiation. With this mode only we are enjoying the solar energy. Okay, so from the sun. Okay, how it is reaching by radiation only. Okay, then coming to the what are the different theorems we have, laws we have which support the radiation. So the theoretical foundation of the radiation was established in the year 1864 by the physicist James Clerk Maxwell. Okay, so he postulated that the accelerated charges are changing of electric currents gives rise to electric and magnetic fields that you know all. Okay, so these rapidly moving fields are called what? Electromagnetic waves or electromagnetic radiation. Okay, and they represent the energy emitted by matter as a result of the changes in the electronic configuration of atoms and molecules. Okay, so this is the physics involved in the radiation. One more time I'll repeat. Okay, so here what do you mean by this particular electromagnetic radiation, electromagnetic wave radiation? Okay, so the energy emitted by matter as a result of the changes in the electronic configuration of atoms or molecules. So in the year 1887, Heinrich Hertz, so he experimentally demonstrated the existence of such waves. Okay, so he predicted this. Who? James Clerk Maxwell. Okay, so experimentally he proved. Who's that fellow proved? Heinrich Hertz. Okay, experimentally he proved that. So there is an existence of such waves, electromagnetic waves. Okay, so electromagnetic waves transport energy just like other waves. Okay, so wave is nothing but water which transport energy, different forms of energy. We have a tidal waves, so many different waves and all we know that. Okay. But here in the radiation, we are talking about what? Electromagnetic waves. So all waves travel at speed of light in vacuum. All the electromagnetic waves travel at the speed of a light in the vacuum. So which is represented as C suffix naught is equal to 2.9979 into 10 to the power 8 meters per second. Okay, so generally this particular electromagnetic waves are characterized by their frequency mu or the wavelength lambda. Okay, and these two properties, this particular frequency and wavelength, okay, so in a given medium are related by lambda is equal to c by mu. So with reference to this particular relation, small problems may be asked. Okay, so do remember this particular formula, lambda is equal to c divided by mu. Okay, and where c is the speed of propagation of wave in that particular medium, which may be given in the problem. Okay, or experimentally we can able to, we require the sophisticated experimental setup. So to identify this particular speed of propagation of wave in the medium. Okay, so this particular speed of propagation in a medium, which is related to the speed of light in the vacuum. So this relation also important. C is equal to C naught divided by N, where C naught is what? What is the value? Speed of the light in the vacuum 2.9979 into 10 to the power 8 meters per second, and this should be remembered, and which may be available in the data book, but in the competitive exams you are not supposed to use the data book. So in that particular case, you must remember this particular value. C suffix naught is equal to, it is nothing but what? Electromagnetic waves travel at the speed of light in a vacuum. So which is a C naught is equal to 2.9979 into 10 to the power 8 meters per second. Okay, so this particular value you have to remember. But the speed of propagation of a wave in a given medium, how do we can calculate it? C is equal to C naught divided by N. So where C naught is nothing but what? Speed of light. Then N is what? Index of refraction of that particular medium. Index of refraction in that particular medium. Okay, so N value may be given, C naught may be known to you. In that particular case, C can be calculated. Then lambda, we can, whatever may be the unknown they are asking, okay, we can able to calculate. So this sort of questions you can expect in the gate examination. Those are writing, put concentration on this. Lambda is equal to C divided by mu. Okay. So generally, this particular refractive index, which is 1 for air and most of gases. And suppose glass you take. Okay. So this particular refractory index may be 1.5. And if you take, for example, water, which may be 1.33. Okay, so the commonest and quite mostly used material medium we have, no, for that the refraction index you must remember. Okay, all we cannot able to, just for air, gases and liquids, particularly water and glass. So these are the general values, sometimes which may not be given. So remember that the refractive index for air as well as most of the gases which may be unity, and for glass which is 1.5 and 1.33 for water. Okay. Next, before that, just we will some more points here. So here the wavelength. What are the units for the wavelength? Micrometer, mu m. Okay. So or micron we can call. So where 1 micrometer is equal to 10 to the power 6 meters. Okay, so here, unlike the wavelength, the speed of propagation, the frequency of electromagnetic wave depends only on the source, and which is independent of the medium through which the wave travels. Okay, so the frequency of electromagnetic wave can range from less than 1 million hertz to the septillion hertz or higher, depending upon the source. Okay, so here the electromagnetic radiation as a propagation of collection of a discrete packets of energy. So those are called the photons or quanta we can say. Okay, so which is proposed by the Max Planck in the year 1900 in conjunction with his quantum theory. So quantum theory, about the quantum theory, the basic idea you might have in the physics you might have learned. So anyhow we will discuss while discussing the Planck's law. Then coming to thermal radiation. So electromagnetic spectrum we will look into. See here Although all the electromagnetic waves have the same general features, the waves of different wavelengths differ significantly in their behavior. So the electromagnetic radiation, generally if you see in practice, which covers a wide range of wavelengths, so which is varying from less than 10 to the power minus 10 micrometers, see for cosmic rays, okay, to the more than 10 to the power 10 micrometers. So those are electrical power waves. Okay, so the electromagnetic spectrum, if you observe here in the figure 6.3 for different wavelengths I have shown you here. Okay, so which includes the gamma rays, X-rays. So this is the gamma rays, X-rays, ultraviolet radiation, visible light, okay, infrared radiation, see here, infrared radiation and thermal radiation, microwaves, radio waves, radio TV waves, okay. So everything is shown here for different ranges. So different types of electromagnetic radiation are produced through various mechanisms. See, for example, here you take the gamma rays. So generally these particular gamma rays are produced by the nuclear reactions. Okay. So generally these particular X-rays, how do we produce? By the bombardment of metals with high energy electrons. Okay. And these microwaves, the microwaves, okay, by special types of electron tubes such as klystron and magnetrons. So again coming to the radio and TV waves. Okay, so these are by the excitation of some crystals or by the flowing of alternative current to electric conductors. Okay. So these are the different mechanisms involved, but all we are not learning in the radiation. Okay, so generally the radio, TV waves, electronic engineers, communication engineers, they pay their attention. So electrical engineers, they pay their attention. So generally, the short wavelength gamma rays and X-rays. So they are primarily concerned to the nuclear engineers. We are not giving concentration on that. And while the long wavelength microwaves and radio waves are concern of to the electrical and electronics engineer. So generally, the type of radiation we mechanical engineers we are focusing our attention is thermal radiation. Okay, so why we are focusing our attention to the thermal radiation only? It is because these radiation is emitted as a result of energy transitions of molecules, atoms, electrons of a substance. Okay, so the temperature is the measure of the strength of this particular activities at the microscopic level, and the rate of thermal radiation emission increases with increasing the temperature. So that's why we are focusing our attention on this particular thermal radiation only in between 10 to the power minus 1 micrometer to 10 square micrometer only. Okay, within this particular limit only we are concentrating. Okay, so remaining all this particular, if you look into the spectrum, electromagnetic spectrum for entire range, we are not putting concentration. Okay. Then coming to here, the thermal radiation is continuously emitted by all matter whose temperature is above absolute zero temperature. Okay. So this is very important point. So we are moving the cursor. Thermal radiation is continuously emitted by all matter whose temperature is above absolute zero. Okay, so that is everything around us, such as your walls, furniture, your friends, your mother, everything constantly emits or absorbs radiation. Okay, so the thermal radiation is also defined as a portion of electromagnetic spectrum that extends from, see here, look into the figure number 6.3. Okay, what is the range of thermal radiation? See here, 0.1 to 100 micrometers, 10 to the power minus 1 micrometer to 10 to the power 2 micrometer, that is 0.1 to 100 micrometer. So this is also very important objective question in the competitive exams. Okay, so the one more time I'm repeating, the thermal radiation, how do you define? So which is a portion of electromagnetic spectrum that extends from 0.1 to 100 micrometer. Okay, so here the radiation emitted by bodies due to their temperature falls almost entirely into the wavelength, in this particular wavelength range only. Okay, so the thermal radiation includes the entire visible and infrared radiation as well as a portion of ultraviolet radiation. See here, observe here. See the thermal radiation which is from 10 to the power minus 1 to 10 to the power 2. Okay, so some portion of ultraviolet we are covering. Okay, some portion, and the entire length of visible region we have. Okay, and infrared as well. Entire length of visible, infrared, and some portion of ultraviolet here. Okay, so thermal radiation includes all these particular three waves. Okay, students, are you following? Any doubts, sir? You are following? Then I'll continue.
Yes, ma'am.
Okay, now here what we call light. Generally we call light. What is light? Light is simply the visible portion of your electromagnetic spectrum. So that lies between, see here, visible here, in between 0 point minus 1 to 1. In some range the visible spectrum is there, but clearly that graduations and all I didn't mark here, but do remember, so which is in between, which lies in between 0.40 and 0.76 micrometer. Okay, 0.4 and 0.76 micrometer. Okay, so in that particular range only spectrum lies, the visible portion. So generally the light is characteristically no different than other electromagnetic radiation, except that which happens to trigger the sensation of seeing in the human eye. Okay, so here the light or visible spectrum consists of a narrow bands of color, so from violet to red. Okay, which are colors. Okay, so which is violet means, I'll show you one more diagram while explaining the Planck's law. Okay, so for different wavelengths, different colors of different wavelengths, so how we can able to, our naked eye can able to detect that particular sensation of seeing these colors and all. So here the violet generally, which is a 0.40 to 0.44 micrometers, to red 0.63 to 0.76 micrometer. Okay, so I forgot to add that particular table, the wavelength ranges of different colors. In the next class I'll add that particular range for your interest only. Okay, so that may not be asked in the examination. So that VGR colors we have, no, violet, blue, green, yellow, orange, red. Okay, so wavelength band we have. So for violet, how much is the wavelength band? For blue, how much is the wavelength band? Like that, for different colors, different wavelength bands we have. But the starting color is violet, is it not? The ending color is red. Okay, but in between the visible spectrum we have 0.40 to 0.76 micrometer. So in that particular range only our eye can able to sense this particular colors. So this is about the brief overview of electromagnetic spectrum, and I'm concluding this. So here we are paying our attention on the thermal radiation only, because where the temperature is involved, that only, because in the heat transfer particularly, even solar also we are not going. Okay, so in particular, in this particular thing only we are going. Then coming to here, in the, as I have said earlier, in the heat transfer studies, we are interested in the energy emitted by bodies because of their temperatures only. One more time, I am repeating. Okay. So that's why we are limiting our discussion to thermal radiation. Okay. Simply we call it as a radiation. Thermal radiation, we are not further, we are not calling. By default, it is a radiation. Okay. So the relations developed below here, whatever discussions we are making related to that only. See here, the electrons, atoms, and molecules of all solids, liquids, and gases above the absolute zero temperature, which are constantly in motion. See, below absolute zero temperature, which are in freezing mode. Okay, so above absolute zero temperature, which are constantly in motion, whatever may be the material they are giving, whether which may be a solid or liquid or gas, so which consists of electron, atoms, molecules, all of you know that. Okay, so above the absolute zero temperature, which are constantly in motion, so that as we can say that the radiation is constantly emitted. So not only emitted as well as which is being absorbed and transmitted throughout the entire volume of matter. Okay, so here the radiation generally it's a volumetric phenomenon. It's a volumetric phenomenon. Okay, but if you take the opaque solids, opaque means what? Non-transparent, like your wood, your wall, non-transparent. Okay, so for opaque solids like your metals, wood, rocks. Okay. So the radiation is considered to be the surface phenomenon. For example, if you observe this particular figure 6.4, this is an opaque solid, non-transparent solid. Okay. So whatever energy pockets we have, see here, once it has reached inside the system, so which cannot be emitted outside. So here, the radiation emitted by the interior regions can never reach the surface. Okay. So the radiation incident on such bodies usually absorbed within a few microns from the surface, within a few microns from the surface. And here, see here, the radiation emitted, generally we are representing like this, the arrow mark directions. Okay. So noting that here the radiation characteristics of the surface can be changed completely here by applying the thin layers of coatings on them. So depending on your requirement, that's what recently if you see the kitchen ware and all, cookware and all, they are putting some non-stick properties and fast heating, uniform distribution of heating, some coating materials they are applied. So in order to improve its emissivity of that particular surfaces, they are putting the coatings. Okay. Then if you apply a thin layer of coating on them, the radiation characteristics of the surfaces can be changed. Okay. So do remember here, though the radiation is a volumetric phenomenon, but for a opaque surfaces, that is non-transparent or solid surfaces, okay, so which is a surface phenomenon. So this is also very important bit to remember, all of you. Okay, so this bit may be asked for a opaque or non-transparent medium, the radiation is considered to be volumetric phenomenon or surface phenomenon. So it is a surface phenomenon because the radiation emitted by the interior regions can never reach the surface, and the radiation incident on such bodies usually absorbed within a few microns only from the surface. Okay. So the radiation in opaque solids is considered as the surface phenomenon. That must be remembered. So here in the figure 6.4, that's what here I have written. The radiation emitted only by the molecules at the surface can escape the solid. So once it is trapped inside, which remains inside only, cannot able to come out. Okay. So in general, in practice, that particular absorption in the wood or whatever may be the non-transparent solids, up to certain microns only this absorption characteristics. Okay. And obviously the emission characteristics, which are at the surface level only, not interior level. That should be remembered. Next, black body radiation. What is black body? Why we consider this particular black body as an idealized black body, idealized body? Okay, then what is the difference between the idealized black body and ordinary black body? Okay, only the bodies which are in black color can be treated as black body, or which is having the characteristics of black body, or even the bodies which are in bright in white in color, so which can also be treated as black body. Okay, our black bodies are exist in nature. So these are the different questions. First of all, immediately you will get what is this particular black body. The body which is in black color, black in color, can be treated as a black body. Okay, so these are the different questions they may come or ask to you. Okay, then what is a perfect definition of black body? Which body can we call it as a black body? So to understand that particular question, let us look into this particular theory, black body radiation. Okay, so a body at a temperature above absolute zero emits radiation in all directions. That already I have told you many times. Over a wide range of wavelengths which emit radiation in all directions. So the amount of radiation energy emitted from a surface at a given wavelength, okay, depends on the material of the body and condition of that particular surface as well as the surface temperature. Is it not? Suppose you take the materials, you take the glass, you take the metal. Metal are different varieties we have, types we have, iron we have, copper we have, bronze we have, silver we have, different. Again, the surface characteristics, if you take, certain surfaces are very smooth, polish finish we have. Okay, some surface roughness we have, different varieties of material with the surface conditions we have and surface temperature we have. Okay, so therefore different condition of its surface as well as its surface temperature. So the amount of radiation emitted, energy emitted from a surface depends upon all these particular factors. Okay, so here the different bodies may emit different amounts of radiation per unit surface area, even when they are at the same temperature. Suppose four bodies of different material, different composition they have given you, though they are at same temperature. Suppose you are at present you are in a room. Okay, so around you chair may be there. Okay, wall may be there and wall clock may be there. Okay, suppose if you sense the temperature, all bodies temperatures are same, but these particular bodies, they emit different amounts of radiation per unit surface area. Are you following? So thus it is natural to be curious that generally we will get the curiosity. Then what is the maximum amount of radiation that can be emitted by a surface at a given temperature? Okay, in front of you one book is there, in front of you one mobile is there, in front of you are there. Okay, your birva is there. So many bodies are there. Okay, but you consider that all bodies are at same temperature. All bodies are at same temperature. Then we will get a curiosity that which body is emitting the maximum radiation. Okay, so the maximum amount of radiation that can be emitted by a surface at a given temperature is nothing but a black body. The black body only gives you the maximum amount of radiation, so which can be emitted by a surface at a given temperature. So it is a idealized body. Okay, so that serve as a standard against which radiative properties of a real surfaces may be compared. See, in the engineering studies, so one standard system we are selecting, and then with reference to that particular standard system, the real system we are comparing, Okay, so by comparing like that, the real system with the standard system, so this real system is so and so efficient when compared to the standard system. So even in the radiation studies also, we have a body, so which give you the maximum amount of radiation at a given temperature. So that body we are calling it as what, a black body. Okay, so this particular black body can be treated as a standard of comparison of your real surfaces. So many real surfaces we have, and we would like to study their emissivities. Okay. Then how would like to conclude that the emissivity of your stool is this much, your book is this much. By comparing with the respect to the black body, we are saying that emissivity is so and so. So that is a black body. Okay, so a black body, how do you define? A black body is a perfect emitter and absorber of radiation. So at a specified temperature and wavelength, no surface can emit more energy than a black body. No surface can emit, okay, more energy than a black body. And a black body absorbs all incident radiation. A black body absorbs whatever radiation is incidenting, which absorbs. So regardless of wavelength, whatever may be the wavelength and direction, which absorbs. Okay. And also a black body emits radiation energy uniformly in all directions. See, which is shown in the figure. See, so this is the black body and this is the real body. See the distribution here. See the distribution here, non-uniform, and here it is uniform. Okay, so a black body emits radiation energy uniformly in all directions per unit area normal to the direction of emission. It's shown in this particular figure. So that's why a black body is a diffuse emitter. We can say that it is a diffuse emitter. Okay, diffuse means independent of direction. Do remember all of it. Diffuse emitter. The term diffuse means what? Independent of direction. Okay, so that is the comparison between this particular real body and black body. Okay, students. Next slide. Then how do you quantify this? Quantify means how much amount of radiation energy is emitted by a black body. What is that particular value? So as an engineer, we have to quantify this. So for which one law we require. Law states that what are the parameters which depends on that particular radiation energy, and we have to relate that particular parameters. Okay, so the law is nothing but the law which relates this particular parameters, and its mathematical statement one should know. Then only we can able to quantify how much amount of radiation energy is emitted by a black body. Is it not? So here the radiation energy emitted by a black body per unit time per unit surface area was determined by experimentally this fellow Joseph Stephen. Okay, so in the which year? In the year 1879, and he expressed as E suffix b of t is equal to sigma t to the power 4. Stephen Boltzmann law. So already I have introduced this particular law in the while we are studying the first unit, mechanisms of heat transfer. Is it not? So here where sigma is what? Stephen Boltzmann constant. Even experimentally we can able to determine the Stephen Boltzmann constant. In our heat transfer laboratory we have experimental setup, Stephen Boltzmann law setup we have. But in a given semester our experimental work are limited to 8 only. That's why I didn't include this particular Stephen Boltzmann law experiment. So here sigma is equal to what? 5.678 10 to the power minus 8 watt per meter square Kelvin to the power 4. Where T here is the absolute temperature of the surface, and this relation was theoretically verified in the year 1884. So this expression was derived in the year 79, and after 5 years Ludwig Boltzmann. Okay, so he has given Stephen Boltzmann law. So where EB is called what? A black body emissive power. Black body emissive power. Okay, so here by seeing this particular expression number 1, we can say that your emission of thermal radiation is proportional to the fourth power of absolute temperature. Fourth power of absolute temperature. Okay, so although a black body, generally when we say a body is black, okay, so our naked eye, if a body color appears as black, then we can call it as a black body. Is it not? But here we should make the difference between the idealized black body and ordinary black surface. So don't feel that all the black surfaces are idealized bodies which emits maximum amount of radiation. You should not consider like that. Okay, so there is a large difference between the idealized black body to the ordinary black surface. Okay. So any surface, whatever may be the surface, that absorbs light. Light is water. What do you mean by light? The visible portion of radiation. Okay, any surface that absorbs light would appear black to the eye, and a surface that reflects it completely would appear white. One more time I repeat, it's a very interesting point. Listen carefully. So any surface that absorbs light, light is nothing but the visible portion of radiation, would appear black to the eye. Okay, and a surface that reflects it completely would appear white. So consider that the visible radiation occupies a very narrow band of spectrum, that is 0.4 to 0.76 micrometers, right? Okay, so we cannot make any judgment about the blackness of the surface on the basis of visible observations. Suppose we have charcoal. Charcoal is in black in color. Boggu, andariki telusinde kada boggu, which is in black in color. So we cannot conclude that it is an idealized black body. Okay, so we cannot make any judgment about the blackness of surface on the basis of visible observations. So for example, take your snow. All of you know the snow and white paint, white color paint, which reflects light and does appear white. Is it not? But they are black for infrared radiation. Your snow ante telusu kada andarki. Okay, and white paint, so which are black for infrared radiation. So they strongly absorb the long wavelength radiation. So they strongly absorb the long wavelength radiation. Okay, the surfaces coated with lamp black paint, the surfaces which are coated with the lamp black paint, so which approaches idealized black body behavior. Okay, so don't conclude that the objects which are in black in color, okay, are all are idealized black bodies. Okay, so though certain objects whose color may not be black in color, okay, so we should not no need to say that those are not idealized black bodies. The best example what I have given you, the snow and white paint. Okay, so which are essentially black for infrared radiation, and they strongly absorb the long wavelength radiation. Okay, so any surfaces coated with a lamp black, any surface, any white color surface, any blue color surface, red color surface, which are coated with a lamp black paint, which we can able to approach the idealized black body behavior. Particularly industry applications or whatever may be the application where you require the emission characteristics, high emission characteristics you require. So wherein we have to put that particular lamp black paint coatings, we have to surface coatings we have to provide. So another type of body, just I'll discuss this. So another type of body that closely resembles to a black body. Here one more diagram I have shown you is a large cavity with a small opening. See here, large cavity. shell-like system, arbitrarily shaped system I have shown you. ఇక్కడ ఏంటంటే ఇంతవరకు మనము బాడీస్ గురించి మాట్లాడుకున్నాము. ఇక్కడ ఇంట్రెస్టింగ్గా ఇంకొక సిస్టము, ఇంకొక బాడీ తీసుకున్నాము. అది కూడా మనకి బ్లాక్ బాడీని రిజంబుల్, ఇంచుమించు బ్లాక్ బాడీ అపియరెన్స్ వస్తుంది. సో ఏ విధంగా అంటే ఇక్కడ చూడండి, మనం ఒక షేప్ తీసుకున్నాం, ఇక్కడ ఒక ఆర్బిటరీ షేప్. ఓకే, సో మనకు ఒక ఫుట్బాల్ లాగా అనుకోండి, అక్కడ చిన్న హోల్ వేసాము ఫుట్బాల్కి. ఒక స్పెరికల్ సిస్టమ్ తీసుకోండి, అక్కడ వెరీ చిన్న హోల్ వేసాము. ఆ చిన్న హోల్లో నుంచి చూస్తే లోపల సర్ఫేస్ మీకు వైట్ కలర్ సర్ఫేసే అయి ఉండొచ్చు, కానీ మీరు అక్కడ కన్ను పెట్టి చూసారనుకోండి, లోపలంతా డార్క్గా కనిపిస్తుందా లేదా, అదే అనమాట ఇక్కడ దాని గురించి. Okay, so another type of body here which closely resembles to the black body, so is a large cavity with a small opening. See here, the radiation coming in through the opening area A, see here, small opening A, okay, will undergo multiple reflections. ఇప్పుడు సపోజ్ ఇక్కడ నుంచి లోపలికి ఒక రే వెళ్ళింది అనుకోండి, ఇక్కడ నుంచి ఒక రే వెళ్ళినప్పుడు ఇక్కడ ఫాల్ అవుతుంది, ఇక్కడ ఫాల్ అయ్యి మళ్ళీ అది ఇక్కడ రిఫ్లెక్ట్ అవుతుంది, ఇక్కడ నుంచి ఇక్కడ హిట్ అయ్యి మళ్ళీ ఇక్కడ రిఫ్లెక్ట్ అవుతుంది, మళ్ళీ ఇట్లా రిఫ్లెక్ట్ అవుతుంది, ఇట్లా అవుతూనే ఉంటుంది, ఇట్లా రిఫ్లెక్షన్ అవుతూనే ఉంటుంది. సో హియర్ the radiation coming in through the opening area will undergo multiple reflections, and that it will have several chances to be absorbed by interior surfaces of the cavity. So before any part which is escaping out. So if the surface of that particular cavity, so generally we are considering as an isothermal at temperature T. Okay. Then the radiation emitted by the interior surface will stream through the opening after undergoing the multiple reflections. Here whatever thing I have written, just look into, so that it will have a diffuse in nature. Okay, so earlier in the previous slide I have told you what is diffuse, meaning independent of direction. So this is also the best example of your black body. Okay, so here the cavity will act as a perfect absorber. The cavity here, which is acting as a perfect absorber. Just 1 second, students.